Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, hi everyone. It's a pleasure to introduce Sasho Nicolò. Sasho is doing a postdoc here this year. He has done a lot of nice work in many areas, including discrepancy, differential privacy, and a lot of things on convex geometry as well. And he's going to tell us something in that area. Okay.
Thanks. Good to give a talk here. So I'll tell you about an approximation algorithm for a geometric problem. And I'll start with the problem because I think it's a natural problem. Please stop me at any time if there are any questions. Okay. It's okay. So here's the problem. So the input is, let me see if I can do this. No. The input is n points in d-dimensional space. And our goal is to find the largest j-dimensional simplex in the convex hull. Okay. So here, those red dots are my points. Imagine this is three-dimensional space. This cube I've drawn is supposed to be the convex hull. And our goal is to find the largest simplex of some given dimension inside that convex hull. Largest I'm measuring by basically volume. Okay, so cool. All right, so we have points, n points in d dimensions. We're looking at their convex hull, and we're looking for the largest volume simplex. So a simplex, a j-dimensional simplex, is just the convex hull of j plus 1 points. Okay, so a two-dimensional simplex is a triangle, a three-dimensional simplex is a tetrahedron, and so on. And we're measuring largeness in terms of volume. Okay, so when we're looking for a d-dimensional simplex, and our points are in d dimensions, we really are just looking for the d-dimensional simplex of the largest volume. If j is less than the full dimension, less than d, it's kind of the obvious thing. So we would look at the flat in which the simplex lies, so the affine span, and we will look at the Lebesgue measure on that flat. So in this case, we're in three dimensions. If we're looking for the largest two-dimensional simplex, we're really looking for the triangle that has the largest area. Make sense? Okay, and to sort of make the problem at least sound more combinatorial, let's notice that we can always assume that an optimal simplex is the convex hull of some subset of the input points of the vertices, right? Because, OK, there might be some other optimal simplex, but you can always just move the points one by one until they snap to an input point without changing the, I mean, there's always a way to do that without changing the objective value, or at least without decreasing it. Does it make sense? So we're really looking for a subset of j plus 1 points from the input that have the largest volume simplex. I mean, whose convex hull is the largest volume simplex. OK, so that's the problem. Good. Cool. All right, so I'm claiming it's a natural problem in computational geometry. It definitely has been studied for some time. You can see it as one example from a general class of problems approximating some complicated object, say convex body, with a simpler one, say, contained inside of it. And you can, in particular, see it as a sort of a polyhedral analog of the largest volume ellipsoid problem. The largest volume ellipsoid problem, or the joint ellipsoid problem, is the same problem, but you're looking to find the largest ellipsoid containing the convex hull of your points. It's also a much harder problem in the representation which I'm working, but that doesn't matter. Okay. Right, and there are some applications of this in low-rank matrix approximation, and also in discrepancy theory, and I'll tell you a little bit about the second application.
Also, does it make sense to actually have lower, like the problem is well defined if I say it's also in the lower dimension of the dominant ellipsoid?
I think you can define it the same way. I'm not sure if people have looked at it. And that's all I can say. OK. All right, so let me tell you about this connection with discrepancy theory. And it's a little bit of a loaded slide, so I'll go slowly over it. So I want to tell you about something called linear discrepancy. That's a measure of how well you can round in a certain sense, which I'll define, how well we can round. So the linear discrepancy of vectors, again, of points v1 to vn in Rd is some measure of how well we can round with respect to these points in the following way. So, all right. So we're given some real weights x1 to xn. Those are real coefficients that correspond to each one of the vectors v1 to vn. And our goal is to round them to, so they're in plus minus 1, but they could be anything. They could be, square root of 2 over 2. But our goal is to round these things to plus minus 1, so to the endpoints, to the integer endpoints, so that the linear combination with the given real coefficients is close to the linear combination with the rounded coefficients. And we say we are measuring closeness in Euclidean norm. So what linear discrepancy is for a fixed set of vectors, what's the worst case error over all possible linear combinations for rounding? Does this make sense? Okay, so that's something that comes up in approximation algorithms, for example, where you solve some linear program, you want to round a solution to a linear program to an integer solution without losing too much. Okay, and what did I write here? Right. So here's the connection to this largest volume simplex problem. So let me denote cursive v sub j, the maximum volume of a j-dimensional simplex in the convex hull of the points. Okay, so here is a theorem. One side, so the lower bound is due to Lovas, Spencer, and Westergombi. The upper bound is due to Matuszek from a few years ago. Doesn't matter exactly what this, this formula is, but it tells you that basically this linear discrepancy is up to log factors equal to some function of these v sub j's. In particular, you can approximate this if you can if you know some approximate values for all these v sub j's. Okay, and also notice that we're normalizing here. So this is j-dimensional volume, so we're raising to the power 1 over j. So this kind of gives the right scaling factor, and this will be nice. You'll see one slide why it's nice for this result.
So
Makes sense?
Is this the reason you want to study this maximum volume problem, or?
That's definitely one reason why I'm interested. I also I realized, so I saw a recent soda paper on that. This is the honest answer, and I realized I already had an improvement, but I just didn't know people care about this problem. So it has been studied in computational geometry for some time. I guess you could argue it's natural on its own. For me, as far as applications, this is sort of maybe the main application I'm interested in.
But it's natural, like the joint ellipsoid that you need from many applications.
I think it's a natural problem. I could dig out more applications. The connection to low rank approximations is also interesting, but it would have taken a little more time to kind of define what it is exactly.
This log D in the upper bound, do you know if that's optimal or?
Probably we know that I need to think about it a little bit for exactly this measure. I think it's not known to be optimal, but some polylog factor is necessary. Yeah.
But the j to the 3 half, and why 3 half?
Yeah, that's a good question. So it's a little hard to answer without going into a proof. So the lower bound at least is some covering argument, and that's kind of what comes out. So you're covering like one object with simplices basically, or something like that. And when you compute the volumes, that's what comes out. It's some function of the volume of a unit ball and the volume of a sort of regular simplex. I need to think about it a little bit. When you normalize the volume to the 1 over dimension, maybe it's the ratio of the two, and which is what comes out of like when you just do the obvious volume lower bound for covering. Does this make any sort of sense? I can think more about it and come back to you. Okay, so it's not the ratio of the two, but it's some function of those two things. Okay, so let me move to the main result, unless there are more questions. Okay, so here's what I want to prove. Here's what I prove in this work and what I'll talk to you about. So I'll show that there exists a deterministic polynomial time algorithm that approximates the volume of the largest j-dimensional simplex up to a factor which, okay, so the analysis exactly gives this j to the j over j factorial under square root. And this, by Stirling, is sort of like e to the j over 2. Okay, and notice that here we always take vj to the 1 over j. So that observation and this approximation factor gives us a constant factor approximation to this linear discrepancy problem. Right? Sorry, it gives us a constant factor approximation to this volume lower bound for the linear discrepancy problem. It gives us log approximation to the actual linear discrepancy problem. Also, this this constant to the dimension sort of approximation factor is optimal. Is the optimal kind of approximation you can get in the sense that we know that the approximation cannot be better than exponential in the dimension. So there exists some constant bigger than 1, such that this problem is NP-hard to approximate better than the constant to the j, to the dimension. Okay, this constant is really much closer to 1 than e, so it's still not clear what the right constant is there. But at least we get the right order of dependence. And this NP-hardness is true as long as, so obviously if j is constant, you can just brute force the problem. So this NP-hardness holds as long as j is sort of big enough. Okay. Again, polynomial time here means polynomial in both dimension and number of points. This is not the usual computational geometry setting where we are in the plane, because then the problem becomes sort of too easy. And it's a significant improvement on what we knew before. So previously, for general j, we knew j to the j over 2 approximation. I'm losing some constant to the j here. This was due to Kachian and Packer. And very recently, oh, I forgot the reference. OK. The Summa, Fritz Eisenbrand, and a few other people. That's embarrassing, sorry. I apologize to Fritz and everybody else. So they improved this only for the case where you're looking for the largest d-dimensional ellipsoid. So only for the full dimensional case, they get something which is like log d to the d over 2. And this is a Soda 2014 paper, 2015 paper, the last Soda. Right, and so we improve on those two results, I think, significantly. This is the main result. Any question? OK. So I want to first tell you about the d-dimensional case, because that's easier. It contains a lot of the intuition. And I want to give you as much of a full proof as I can in sort of the time that I have for this case, because I think it's simple enough. OK, so I'll go slow. Please stop me again if you have questions. OK, so here's some simple sort of reductions that we can do the problem to make it slightly easier. Okay, so there are a bunch of them. So I'll go sort of slow over them. So let me use the delta, because it looks like a triangle, to be the optimal simplex. OK, so it's the convex half of some subset of d plus 1 points from the input. Let's guess the first vertex. Okay, we can always do that. There are only n options. In reality, what we'll do is we'll just kind of run over all the options. I mean, we'll run the algorithm once for every option. But for now, let's assume we just know the first vertex. Someone tells us what it is. And let's replace each point vi. So by replace, I mean, let's just move each point. OK, yeah, let's just subtract the first vertex vi1 from each point vi. So this just kind of shifts the whole set of points. So it obviously doesn't change volumes. But now we know that one of the optimal points is the origin. It's just convenient. It's convenient. You'll see in a second why. But now after we do this, the new problem is to find not d plus 1, but only d points from the input. So a subset of d points from the input. So that the volume of the convex hull of these d points and the origin is maximized. Okay, and that's convenient. just because it lets us make the problem a linear algebra problem as opposed to a geometry problem. Okay, so this is equivalent to, we have our points. So let me write something. Okay, so we have our points. And let's sort of think of this matrix. Maybe A is not the right thing. Sorry about that. Matrix V, which is just the matrix which has columns which are the points, except the 0 point, which we don't care about anymore. Okay, so V2 and so on. Okay, and now I'm claiming that this problem of finding these D points that whose convex hull together with 0 has the largest volume is the same as finding D by D. So okay, so here the dimension is, this dimension is D, and this dimension is N. Okay, so that problem is equivalent to the problem of finding a D by D submatrix of this. It has the largest determinant in absolute value. Why? Because the volume of this thing is just equal to the volume of the corresponding submatrix times a scaling factor that doesn't, sorry, the volume of this is equal to the absolute value of the determinant of the corresponding submatrix times 1 over D factorial. That's, yeah, let's just take that on faith. I mean, I think that's convincing for everyone, right? Okay, cool. All right, so now we have this problem. We just have this N by D matrix, and we want to find a D by D submatrix of it that has the largest determinant in absolute value. That's our problem right now. Let's just do one more simplification, and then we're kind of, okay, almost done. Let's just add also the inverse, I mean right. Let's add, so after doing this first transformation, now let's also add minus vi for every vi. Okay, what this lets us have is that it makes the set of points symmetric around the origin. That's just kind of convenient. It also obviously doesn't change the optimal solution. Why? Because, okay, let's see. So, so if we take a submatrix that has both vi and minus vi, the determinant is 0. So okay, so we always, so for a non-zero solution, we always take either vi or minus vi. But which one we take just changes the sign, and we're taking absolute values, so it doesn't really change the value of the optimal solution.
If you think of it in terms of the volume, seems like
so.
increase.
But now okay, so remember we kind of changed the problem so that we always take the origin to be one of the vertices. So say we're just looking for the optimal two-dimensional, sorry.
Or 3-dimensional.
Well, it's kind of, yeah.
So imagine that two points are very close to each other.
Let's just do two-dimensional, right? So we look at this and this.
2-dimension, it's always a.
So my point is that this triangle and this triangle have the same area.
Because sort of the length to the right. So if we have some kind of base and one vector, we only care about sort of the height, kind of the distance.
Right. So why are they the same? Because this length and this length are the same, and the height doesn't change when I do this. And you have the same for sort of larger dimensions. You always have like base times height. Okay. Cool. All right, so now those are the basic transformations. Now I want to sort of move towards the actual algorithm a little more. Okay, so we are approximating a hard maximization problem. Okay, so the usual game is to find an upper bound on the optimal solution. Then we'll compare how well our algorithm does against that upper bound. I am worried that Muhi doesn't seem convinced. Okay, fine, cool. So here's the basic upper bound we use with some modification. So here's one Oh, this doesn't have. OK, cool. Here's one upper bound that we have available. Again, remember, we have this problem now of finding the largest determinant of a d by d of a square submatrix. OK, so I'm claiming that one thing that's true is that if all columns have length at most r of this matrix, then, well, any determinant of this matrix has absolute value at most r to the d. And that's just Hadamard's inequality, basic statement about determinants in matrices. Okay. All right. So that's clearly not a good upper bound because, right, so our points could look like, well, like this, I guess. But I mean, our points could look like this, right? So we could have, maybe a few long points. I mean, a few a few long vectors that are far from the origin, and a bunch of really tiny ones, right? And say we just have one big guy, right? So now this upper bound would be huge because of just this guy, but you obviously can't get something that's comparably large in terms of an actual simplex, right? So it's not a good upper bound itself, but we'll fix it somehow. Product of what?
The norm of the VI?
But he doesn't know which one, right?
But you can maximize. Okay, but a better upper bound is to maximize over all subsets of size d. The product of the VIs.
Can you compute that? I guess you could compute that. Yeah, that's probably also not very good.
Just take a log, right?
That's probably also not very good because they could be pretty close together and it'll still be a problem. You could have a bunch of long ones, but they're very close, so it's still right. All right. So here's something we'll do to try to use this upper bound. Okay. So I'll introduce one more object, which is the Launer ellipsoid of this set of points, so of the columns of this matrix. And by that, I mean the minimum volume ellipsoid that contains all the points. Okay, and because we did this transformation that makes sure that our set of points is symmetric around the origin, we can also assume that the minimum volume ellipsoid by sort of a standard argument is centered at 0 as well. Okay. So I mean, it will be centered at 0. Okay. So how do we use that? Okay. So the point of this is that it sort of fits tightly around our set of points. So we want to kind of use that. Okay, so here's what we'll do. So this is what it looks like. But we have our upper bound, which is somehow in terms of L2 norms, so in terms sort of containing things in a sphere. So we want to kind of map this whole thing to a sphere. So what we do is the following. So we have this ellipsoid EL, which is the minimum volume ellipsoid that contains our set of points. We can always compute a linear map that maps this ellipsoid to a ball, to a standard Euclidean ball. And we can also do that with a linear map that actually has determinant equals 1, so it doesn't change volume of any sort of. I mean, it just doesn't change volume. So
you mean the original volume is also 1?
The what now?
The volumes of the spheres should be the same.
Yes, the volume of the sphere would also not change, yes. The volume of the sphere would also not change, and the volume of any simplex, any full-dimensional simplex would also not change. Because the determinant of this linear map, say as a matrix, is 1. Okay, so that means that R in particular has to be the product of the axis lengths of this ellipsoid to the power 1 over d. Okay, this makes sense. I thought that something was wrong with that statement. Okay, so what we do is that we compute the smallest volume ellipsoid. That's a convex program. We can do it up to any approximation. Believing that approximations are fine for us. It's not immediately obvious, but they are. And right, then we'll compute this linear map, or in other words, I mean, this ellipsoid will be given by either this map or its inverse. Right, so, and then we just do this transformation where we apply this map to each point in the input, each VI. And now we have that the Launer ellipsoid is a ball of some radius r, and our upper bound will be the radius to the power d. Okay, because we just applied this linear map that doesn't change volume, and it's a valid upper bound here after the transformation. and the transformation didn't change the value of any solution, this is a valid upper bound. Does that make sense? Questions?
So it is just the product of the eigenvalues.
In other words, it's just the product of the eigenvalues. Yes.
To some scaling.
It is just the, yeah, for the determinants, actually, it is just the product of the eigenvalues. And that's another, or like the product of the axis lengths of this ellipsoid. So that's another way to see this upper bound. So not sure which is easier. Maybe what you're saying is easier, actually. Okay, kind of one reason why I did with this transformation is I wanted to give some intuition why it's a good upper bound. And the point is, again, that, well, the smallest volume ellipsoid somehow has to fit tightly around the set of points. Why? Because if it doesn't, so if our points don't sort of touch in some vague sense the ellipsoid in every direction, so if there's some direction where there's big gaps, we can kind of squeeze the ellipsoid and get a smaller volume. This is sort of the rough intuition why, you know, this does give you some information about how, well, remember the bad example for the upper bound was sort of these thin bodies, so we want to kind of avoid that, and this is why this sort of helps. And so one nice thing about the Launer ellipsoid that was used in previous algorithms, but is sort of too weak for the kind of result I prove, is that, so one thing we know is that, OK, if we have some convex body whose Launer ellipsoid is a ball of some radius r, then if you scale the radius by, oh, and it's a symmetric body as well. If you scale the radius by root d, then you get a ball that's guaranteed to be contained in the convex body. It's not guaranteed to be contained as tightly as it is here, but it's always going to be contained. OK, so that's one thing that tells you that sort of the upper bound is good in the sense that, well, this convex hull has to contain sort of large things because it contains this relatively large ball inside of it. And this was used by previous algorithms, but it's not quite good enough for us. But what I'll use is sort of the fact from convex optimization that lets us prove something like that. In other words, I'll use the dual of the Launer ellipsoid. Okay, so this is what we get from convex duality about this Launer ellipsoid. This is sort of a dual characterization of what the ellipsoid is. So you can say this is, I mean, I guess this is John's theorem in some restatement. And here's what it says. So it says that if the smallest volume enclosing ellipsoid of OK, it says that the smallest volume enclosing ellipsoid of the convex hull of points v1 to vn is a ball of some radius, if and only if there exist non-negative weights that you assign to the points, so that the sum of Ci times these outer product matrices, I mean this rank 1 vi transpose matrices, has to be equal. So OK, so the smallest volume, so the Launer ellipsoid is a ball of radius r if and only if there exist weights such that this thing is equal to the radius squared times the identity matrix. OK, so the intuition is that, I mean, this is what comes out. Oh, and you also, and the other thing is that the weights have to sum up to d. OK, this is just what you get from writing down the KKT conditions for the smallest volume containing ellipsoid problem. That's one way to look at it. If you want some intuition, except just the manipulations to get the dual, this sort of says that these VIs have to sort of point in all kinds of directions in order for you to be able to do something like that. In order for you to be able to decompose the identity in this way. OK? OK, so this is what we use. And the main idea of the actual approximation algorithm is to treat the CIs in some sense as probability weights. Let me show you, that's vague, so let me show you immediately what actually the algorithm is, because modulo this is sort of simple. So the algorithm to actually find approximately largest simplex, d-dimensional simplex, or rather a d by d submatrix of this matrix, would be to sample d columns from the matrix. Each column is sampled independently with replacement, and column I is sampled with probability proportional to Ci. And the Ci's are non-negative and they sum up to D. So the probability of sampling I is just Ci over D. Okay, that's the algorithm. So we compute this Launer ellipsoid. We can also get these weights. Actually, some of the algorithms that compute the Launer ellipsoid first compute these weights. So it's already sort of for free. Then we use these weights to run the sampling algorithm. Okay, this is what I call randomized rounding. Okay, and let's now try to, okay. So let me now slowly go through the analysis in just a couple of slides. So why is this good? So let's compute the expectation of the squared value of a sampled solution. Turns out to be more convenient to work with the squares for some reason. You'll see why that's okay. All right, so let's just write that out. Okay, all right. So what? Okay. So I said I sample with replacement. So if I, but if I sample the same column twice, I obviously get determinant 0. So those don't contribute. So in my expectation, I only have contribution from the terms, well, from the cases when I sampled D distinct things. Okay. So for each such set I could have sampled, I could sample it in d factorial ways. It's just they're all distinct, so they're d factorial ways to sample it. And the probability of sampling exactly those elements is exactly the product of the probabilities because they sample independently. Okay, so this is the probability of sampling the set S. I can sample in d factorial ways, and the value of the set is actually this. So just the squared. I mean, for me, value right now is the squared value, so it's just the squared determinant. Okay. All right, so a few more manipulations. So again, Pi is just Ci over D. So let me just, and all these sets are of size D. So this gives me a D to the D factor up front. And there's also this d factorial that doesn't depend on S. So just things that don't depend on S I've brought up front. So, okay, so I have this. Remember, this is actually the inverse of the approximation factor I'm shooting for. So I want to somehow show that this compares with my upper bound, okay, which is this radius. For the square value, the upper bound is the radius of the Launer ellipsoid, which is in this. We made sure it's a ball to the power 2D now. Okay. Right, and I did just one more thing. So this is right. I just brought the constants in, right? So what I have is some submatrix, right? And I'm taking product of Ci over I in this submatrix, in the sort of index set of the columns of the submatrix, times the determinant of, let me call V as the submatrix. Okay, so what I'm doing, I'm just, instead of having these two things separately, I can just multiply the ith column in the submatrix by its coefficient. But it's not, right, but because I'm taking squared determinants, I'm multiplying by the square root of the coefficient of the column so that I get the same thing. Does this make sense? Okay. So this last step is just sort of bringing those things in. Okay.
Why is it? Why is it that's what you want to show?
Why is that what I want to show? Okay. So this is the expectation of the squared value of my algorithm, of this randomized algorithm. All right, and I said it's equal to this big summation times this factor. So this factor is the approximation factor I'm going to be shooting for. And now I just want to show that this is at least as big as my upper bound on the optimal value. Okay, and my upper bound was this radius of the containing ball to the power D was my upper bound for the biggest absolute value of the determinant, but I'm squaring everything, so I just added squares on both sides. So I just want, right, so this is my approximation factor, and this term I want to show is at least as big as my upper bound of the optimal solution. Yeah?
Well, enough to show. Enough to show.
Yes. Fine. It is enough to, yes. Well, for this approximation, okay, yes, fine. Yes. I agree. I agree. Okay. Does this go? Okay. So let's do that. Right. So we have this summation. So what is this? I've basically, in my matrix, I've multiplied every column by square root ci, so square root c1, square root c2, and so on. And now this summation is sum over all d by d submatrices of the square determinant of the submatrix. Okay, so I want to relate this to this radius using John's theorem. Okay, and this turns out to just be to follow immediately from the Binet-Cauchy identity for determinants. Okay, this is something yeah, right. So it's one of these things, you just write out the formula for the determinant, it kind of follows. Who has seen the Binet-Cauchy formula before? Not really. Yes, two people. Cool. Okay, so let me sort of say it a little more generally. So what it says is that, say you have some matrix A. So and say this matrix looks like this, right? Has this shape. I mean, it actually doesn't matter, but it makes more sense in this way. Okay. So, and I'm interested in the determinant of the matrix times its transpose, right? So the determinant of A times A transpose. Okay. So if A is just like a single row, this is just the inner product, and it's just the sum over all, 1 by 1 submatrices of this row squared, right? So if it's just single A times A transpose, the determinant of this is just, this is just a number, so it's just the number, and this is just equal to sum of AI squared. Okay, in general, this is equal to the sum over, so say this is again D by N, sum of S subset of N, size of S equals D, of the determinant of A sub S squared. A sub S is just the submatrix determined by this set. Okay, so it's sort of a generalization of this thing. Does this make sense? All I can say sort of makes sense for the one-dimensional case. It also makes sense for the case where this is a square matrix, because then it's just the trivial identity. All right. So what this gives us in this case, what we have here is exactly this summation where A is this matrix. And what it tells us is that this is equal to the determinant of this matrix times its transpose. This is exactly this summation of outer products. Okay, and of course, the two square root CIs we can bring together. Now we have this summation of CI times VI transpose. That's exactly what John's theorem tells us, that this is equal to R squared times the identity. And obviously, the determinant of this is just R to the 2D. Okay, so this kind of completes basically the analysis. So what we derived was that the expectation of the squared value of a solution is at least this factor of D factorial over D to the D times, well, R to the 2D, which was our upper bound to the square of the optimal solution. Okay, and again, you can use Stirling to sort of see that this is basically e to the minus D minus little o of D. Right, so this tells us that, okay, this randomized sampling algorithm in expectation gives us something that's good. And good here means sort of large enough. The problem is, I think there are cases where this can give you horrible things except with exponentially low probability. Because, well, you only get an exponential approximation factor here. So I think it's totally possible that with high probability it doesn't give you anything good. So let's not run that algorithm. let's instead de-randomize it. And you can de-randomize it using sort of standard conditional expectations machinery. So once you de-randomize it, the guarantee you get is that you get a deterministic algorithm that has a guarantee at least as good as this expectation guarantee. And that's enough for us. And because it's deterministic, we don't, it just works. I mean, we don't care about probabilities anymore. Right, and de-randomizing is a little technical, but it's sort of standard. You just have to compute the actual conditional expectations. Okay? Okay, so that's the algorithm for the full dimensional case. And I want to a little more vaguely tell you what happens when j is less than d, so when we're looking for less than a full dimensional simplex. That turns out to be a little more technical, but sort of similar ideas work. You just have to work harder. Okay. So first, okay. Give you a second. Okay, so switching context, we're sort of back to the beginning, sort of. So we can do basically the same transformations as before. If we can guess the first vertex of an optimal j-dimensional simplex, again, shift everything so subtract vi1, the guessed vertex, from every input point. And also take the symmetric point around the origin. So now we transformed our problem to, first now because we took both of these guys, now we have a problem that, input that's symmetric around the origin. And now we're looking not for j plus 1 points, but only for j points, so that the simplex they make together with the origin is as large as possible in volume. And again, you can transform this to a determinant problem. And now it's a little, so again, we have this matrix, basically. Let me not put this here. Again, we have this matrix. But now the problem is to find, a D, so D is always the ambient dimension, but we're looking for a D times J submatrix that has the largest determinant. Well, the problem is, what is the determinant of a D plus J submatrix? And you can see that the right thing for the problem is to look at the submatrix transpose times itself. Look at that's a square matrix. Look at the determinant of that and take the square root. This up to sort of a normalizing constant is the same as this volume of the j-dimensional simplex. What is probably an easier way to think of this is that what this is actually just, I guess it would be natural to also define that as the determinant of a rectangular matrix. It's just the product of the singular values. Okay? All right. Where's this? Right, so this is our problem now. We're looking to find a D by J submatrix, our big input matrix. So that this submatrix has large determinant, and by determinant I mean product of singular values, or this thing. Okay. And you could again use the same algorithm as before. It's well defined. You just sample J times instead of D times. And it does give you an approximation factor, but the factor looks like J factorial over D to the D. So if J is pretty big, it's not too bad. It's not too far off from what we're shooting for. But in general, it's not good enough. At least it's not the right order of magnitude, sort of. Okay, so we will need a different upper bound, basically. I mean, it kind of makes sense that this sort of full dimensional, maybe it's not quite clear why it doesn't work, but I'm pretty sure that the Launer ellipsoid upper bound doesn't work immediately. So I'm going to modify it to something that I know works. Okay, so here is the upper bound I'm going to use. I don't know why I said upper bound idea, it's just the upper bound. Okay, so one thing we know, it's not very hard to show, is that if all the points, all the columns of this matrix are containing some ellipsoid E, and well, because our point is symmetric around the origin, we can always assume this is centered at 0. and say the major axes of this ellipsoid are A1 to AD, and I've ordered them by length. Okay, so one upper bound that's true is that this is my value of the optimal solution. That's what I call D sub j. So the maximum determinant of a D by J submatrix. We know that this is bounded by the product of the J longest major axis for any ellipsoid that contains the points. Okay, it's not very hard to show. It's sort of the right analog, say, of this Hadamard inequality plus Launer ellipsoid upper bound. Okay, so let me call this a J-Launer ellipsoid. It's just, sorry. What I call a J-Launer ellipsoid is the ellipsoid that minimizes this upper bound over all ellipsoids that contain the points.
By the way, the W is pronounced like a V.
Lovner.
Like a V.
Like a V. So, but right, should I probably pronounce the umlaut like an umlaut, like an O umlaut? Lovner, I'm not sure I can. Okay. So the J Lovner ellipsoid, let's say, it minimizes, right, this upper bound, so this product of the J longest axis over all ellipsoids that contain the input. So this achieved minimum will be this upper bound that we're going to use for this problem. And I also want to sort of give you an algorithm that competes against this upper bound. Okay, because I cannot give you too much details, maybe as motivation, I'm not sure it's helpful, but let me talk through sort of the most trivial case where we're just looking for the longest, basically, column of that matrix. So it's clearly a trivial problem. We just go over the columns, take the longest one. So I'll give you, an exact algorithm for this problem using sort of the same machinery that I use for the general case. And I shouldn't touch this probably. All right, so the optimal value is the length of the longest column. And my ellipsoid, my optimal ellipsoid is, okay, it doesn't have to be a ball, but you can see that always an optimal solution is a ball in this sort of trivial case. So we're just looking for an ellipsoid whose longest axis, an ellipsoid that contains all the columns of this matrix and its longest axis is minimized. Okay, so in other words, you can just look for a ball that contains all the points and the radius is minimized. And the upper bound is just the radius. Okay, and the way this generally is going to work is, okay, I'm going to write this as a convex program. I'm going to, again, look at the KKT conditions, take the dual. What the dual is going to tell me is that whatever the optimal R is, there exists non-negative coefficients, C1 to Cn, that sum up to 1. So this 1 is this one, right? It's the dimension 1. Remember, in the full-dimensional case, this was D. And what I know about these things is that I can look at the same matrix, summation Ci Vi Va transpose. Now I know that the trace of this thing is equal to the optimal R squared. Okay, but the trace of this thing, well, trace is linear. You can just take it inside, and the trace of Vi Va transpose is just the norm of Vi Va transpose squared. The norm of Vi squared. So what this tells me is that there exist weights so that summation of Ci length of Vi squared is equal to the optimal solution, which is my upper bound. Okay, so now if I sample Vi with probability Ci, this is the expectation, and it's optimal. So this is an optimal algorithm. Take this program, write the dual, solve the dual, take the weights, sample according to the weights. That actually, in expectation, works. Okay, so that's a very bad way to compute a very simple thing. But the thing is, it generalizes for general J. So this is basically what we're going to do. We're going to write the dual of the ellipsoid minimization problem. Okay, and the dual is going to tell us that there exists non-negative weights that sum up to J, where J is the dimension, so that some function that's complicated, I'll tell you what the function is, but for now, take it as a black box. So that some well-defined but complicated function of this same old matrix is actually equal to the optimal upper bound that we get from the ellipsoid minimization problem. Okay, and this, all I'm saying here is that we know that this is an upper bound on the optimal solution. Okay, and what I mean here is sort of the challenge in kind of deriving this whole thing is that for the J-Lovener ellipsoid, when you write it as the solution of a minimization problem, the objective is not, it's convex, but it's not differentiable. So that makes deriving the dual and writing the KKT conditions a little more complicated. It's not a big deal, but it's just a little uglier. And it also makes this function a little more complicated. But the algorithm will be the same. So we'll compute these dual weights, and then we'll scale them down by j so that they give us a probability distribution. We'll sample, oh, I'm sorry, this should be j. We'll sample j times independently with replacement using these weights. Okay, and this will be the randomized algorithm. Again, we'll de-randomize it at the end, but we analyze this.
Why do you sample these replacements?
I guess all I want to say is probably sampling without replacement is, I think it can only do better. It's just I can't really analyze it better. I cannot give a better analysis for that. Okay, so, and why I keep pointing it out, maybe just to be clear that that's what I'm analyzing.
Actually, it's almost the same because for all practical purposes, I can replace every point
That's
by
actually true.
gazillion points and divide the weight.
It's probably true, yeah.
So it doesn't
Yeah.
matter. It's the
Yeah.
same.
I think you're right. Okay. So in general, how does the analysis work? So again, I'll compute. This is the expectation of the sum of squared singular values of the matrix that I get. This is this determinant. Okay, so again, I have, right, so if I sample something twice, that gives me no contribution again, because, right, well, I'll get 0. So I only get a contribution from all the cases when I sample a set of j elements, of j distinct elements. Each such set I can sample in j factorial ways, and the probability of sampling it is the product of the probabilities by independence. And again, I have this j factorial. Should have put it up here maybe, but pi is ci over j, so I get this j to the j as well, because I take a product of j terms. Right, and this is my expectation. Now, before I had this magic, okay, sorry. Before I had, some sort of magic formula that told us what this was in the full dimensional case. Well, now there's some analog of this, which tells us what? It tells us that this big summation is equal to to the degree j elementary symmetric polynomial evaluated with the eigenvalues of this matrix that we've seen before. Okay, so this, you have to believe me for this. That's part of sort of the technical detail, but it's not very hard once you know it. It's a useful fact, basically. Right, so this is the sum. So what's the degree j elementary symmetric polynomial? Okay, I'm almost done. You just, okay, so you have all the eigenvalues here. You just take every subset of j eigenvalues, take their product, take the sum over all of these things. Okay, so this is the expectation. And, right? And once again, this is the approximation factor that I'm going to prove. So what I need to show is that this elementary symmetric polynomial is at least as large as my upper bound. And by duality, I got that my upper bound is actually this function, whatever that is. So I need to compare basically this and this. I need to show that this is at least this. Not a need. It's sufficient to show that this is at least this. It's enough. I don't necessarily need it, but I really like if I can do that. I would really like it if I can do that. All right, so let me just, so that you don't complain that I haven't shown you this, this is the function. I guess maybe it doesn't look so bad. So this is what the function looks like. Okay, so it's, again, the lambda I are the eigenvalues of this PSD matrix. And it turns out to be, you take the product of the top few, top k, And then you take this, it's kind of like an average to the power j minus k. And k is well defined by this. I mean, k is the unique number that satisfies this. You have to, so I had to show, at least for me it wasn't obvious, that this is ever satisfied, but it turns out to be satisfied for a unique k. Okay, and this is the function. It's a little strange.
So it's not differentiable.
Because it's not differentiable, so you get this, yeah. In the duality, you get that some, what's the word, some sub-differential of something is equal to something else. It gets a little. Okay, but what we can, what I can show is that, is that the right thing? Yeah, sorry, this is reverse. Yeah, this is the wrong way. So what I can show is that this function is always bounded above by this elementary symmetric polynomial, and I'll just give you the kind of the keyword there, is that this follows by staring at it and using sure convexity of elementary symmetric polynomials. Okay, so it's sure convexity is a very general tool for proving inequalities. Turns out to be useful here. Okay. All right, so that's it. So in summary, I talked about the first polynomial time algorithm to approximate the maximum j-dimensional simplex problem within a factor which is exponential in the dimension, which is the right kind of dependence for the approximation factor. It gives a constant factor approximation to this determinant lower bound for linear discrepancy. And so there are a bunch of open problems. What's the right constant in the hardness is one problem. For these ellipsoid upper bounds, is this the tight analysis? Is that all they can give? Maybe that's an easy problem, but I haven't thought about it too much. Right, and is the approximation factor optimal? Maybe it is. It's natural. It's this e to the something. I don't know. Okay, so this is for Muhit, and whoever else is interested. But that's what we've talked about a little bit. So, for this, so I'll tell you just very quickly. So the following function is modular. Is a modular set function. So the sets are subsets of the columns of this matrix, and the function is log of the determinant of the submatrix. And again, a determinant, what I mean by determinant is the product of the singular values. Okay, so that's a submodular function. And our problem is really maximizing this submodular function with the constraint that we need to get a set of size j. So the constraint is okay, there you go. Sorry, just a second. So the constraint is that the set you pick should be a basis of a uniform matroid. The problem is that the function that's submodular is a log of the objective function. So to get an approximation guarantee for the actual objective function, I need an additive guarantee for the submodular maximization problem. And I'm not sure, maybe you can get that with sort of standard machinery, but at least using black box results, I didn't quite see how to get it. Does this make sense as far as the connection to submodular maximization? So if you can get it using just submodularity somehow, maybe it can generalize to something else. That's basically why I'm asking. It might also give some intuition what's happening. That's it. Thank you.
Is there okay, so you always present this dual word, which I guess is implicit in this upper bound that you have.
Mm-hmm.
But if I just can we write a convex relaxation directly, which is a relaxation for our problem?
Mm-hmm.
Maybe SDP or LP or whatever.
I mean, that's a good question. So SDP for a volume problem or determinant problem seems a little...
Some convex program.
Some convex program, yeah. So for the full dimensional case, so from the dual you get that. It's just that for the less than full dimensional case, it's a little strange. So for the full dimensional case, it's just maximizing log of determinant of summation ci vi vi transpose. That's convex, right? I mean, that's from
Variables are CI.
Subject to, yeah, variables are ci, subject to summation ci equals d, ci bigger than 0 for all I. So that's, and okay, you can also see immediately that that's a convex relaxation. It's just not how I came up with this, and it's also not, it doesn't allow me to easily generalize it to the general J case, yes. Because as you saw, it turns out that, well, at least if I go the ellipsoid way, the dual that I get for the general case has a much more complicated objective function that I would have never come up with just by looking at the dual. This you could come up with, the full dimensional case you could come up with. Why can you see it's a relaxation? Just the usual way, just take the CIs to be an indicator of an optimal set. It's feasible, right? But yeah. Maybe there's a more general relaxation is what I'm saying. I get. Maybe there's a more natural relaxation that you can come up with without looking at ellipsoids. Yeah, more questions?
Okay, let's thank Sasha again.
Thanks.